Hi, so my name is Teofilo Campos. I'm from the University of Surrey. I also have a foot in the University of Sheffield at the moment. And in the next 3 minutes and a half, I'm going to summarize 3 years and a half of work, which is basically the period we had sponsorship from Pascal and also from the EPSRC. So this works about sports video annotation with anomaly detection and transfer learning, and was done with these collaborators at the University of Surrey. Yeah, that's fine. Yeah. So what we are trying to achieve is basically annotate videos and extract information from video. And we focused on videos of tennis games because that simplifies the problem a bit from a computer vision perspective. But tennis is an interesting kind of scenario because it's governed by a fairly complex set of rules, but they are performed by a small number of agents. So they're basically 2 players, the ball and the court, and the position of the elements on the court. And using computer vision, basically, we can detect the lines and project them into what would be a top view of the court, and this enables us to do a higher level processing. So in the next slide, basically we designed this system which has some cognitive vision kind of inspiration. So at the left, basically we have the lower level processing methods, which basically they deal with large amounts of information. So for each pixel in the whole video sequence, they do some very short-term memory kind of processing to do things like background subtraction. And then as you go to the right there, we detect higher level concepts like players and describe their actions, track the ball, detect the court and do that projection. And then finally on the right-hand side, we combine all these cues so that we can then output higher level description. So at the bottom level, basically, we worry about lots of pixels, and in the final stage, the system would process, let's say, 2 hours of a tennis match and just say, oh, Sharapova has won this game in a very short sentence describing the whole thing. Yeah, so what we are actually interested as well is on the whole idea of detecting anomalies and transferring knowledge from one domain to another. So basically, let's say we have this system that was designed and trained for tennis, and then we present it with input that's actually a badminton match. Badminton also has 2 players, a court structure, and a moving object that looks like a ball. So in terms of low-level vision processing, it's quite easily transferable between tennis and badminton. But that enables us to do higher-level analysis and actually try to update the rules of the game. And given enough data, the hope is that we can then get a system that also adapts for different domains and could then go on to other cart-based sports. And we do the same for low-level action recognition and updating the models of players' actions and so on. So I can talk about more later in the post.
Okay, thanks. Thanks very much.
Hello, my name is Ksenia, and I'm going to present you the work that is done at the University of Helsinki and Helsinki Institute for Information Technology. And this work is done with the supervision of Dorota Glowacka. And so we consider a problem of image retrieval in the database of unannotated pictures. That means that we don't have any keywords associated with pictures or any natural language text. And when the user is unable to query the system by context, we employ the relevance feedback mechanism to navigate in the image space. For instance, consider an example of a journalist looking for a picture to illustrate his article about maternity. And the idea of such an image may be quite vague, and in order to navigate there, he may use the relevance feedback to indicate what pictures are closer to his ideal target in order to move on. And so Move to the next slide. And in the next slide, the data flow in the system is presented, and we employed two-level Gaussian process bandits in order to tackle this problem. And this is a kind of exploration-exploitation algorithm. That means that we want to, on the one hand, we want to exploit the knowledge that we got in the system. We want to explore that limited relevance feedback that we got. But on the other hand, we want to reduce the uncertainty in the system and explore other opportunities. And usually these algorithms are designed to sample only one object per iteration, and the system operates through a sequence of rounds where a set of K images is presented. And the problem of choosing K images is a little bit tricky, and especially when we consider a case of hierarchical bandits, and we use Gaussian process beliefs to use it as a fake feedback in the system to ensure that the set of images is diverse enough. And in order to be applied in the real-life system, this type of algorithms for image retrieval should be time efficient and easily scalable for large sizes of the database. And this question is often ignored by the researchers, and we tackle these problems through using self-organizing map as a discretization of the space, and the self-organizing map is used as a hierarchy in these hierarchical bandits. And, oh, can you go back? Sorry. And you can see from this picture, this is an example of a map. We see that pictures that are close to each other in the grid, they're visually similar. Now, let's and so we analyzed the results. First, I analyzed the algorithm theoretically to indicate what properties they have. Next, we ran a set of simulations to compare it to other algorithms and indicate whether they make sense. And finally, the system was implemented, and currently I'm running a set of user studies with real users to indicate whether they can make use of the system. And we consider a set of tasks for them. And if you're interested, you can come to check my poster, and I can even show you a demo of the system, how it works. So thank you for your attention.
Hello, everyone. I'm Francis Dogbey from Ghana. I work with Professor Balcazar over there. This is about a year work on a rule, association rule. Essentially, what we're trying to look at is that most of the data that we have around, or rules that we generate, are based on a data set. Often, this data set may contain some errors, and this will influence some of the rules that we've generated based on the data set. And so one of the things that we're looking at a new feature that can be used to help in doing some of this work. So, please next. So we take a look at this by looking at the notation with regards to how association rules are defined. Basically, if you take a look at it, X implies A is a basic notation, but that raises two interpretations. One level is in terms of relaxed implication, another one is a standard implication. While the standard implication is too strict, that of the relaxed implication is too loose. And so there are several measures by which it can be measured, and often some of these definitions are also too different to define which one will help most probably. And so our work in this case, please next. We try to take a look at the entire data set, remove a predictive column out of it, and then at confidence level 0, manually adjust the support level and see if we can get a rules of about 20,000. Based on the 20,000 rules, we try to find the exceptions to each of the rules. Based on the exception for each of the rules, we actually define a new column, which is added to the original data set. From there, we submit the new data set or the expanded data set to two predictors in this case, the C5.0 and that of NB. And based on that, we found a few observations that we can discuss with you. Please, next. Okay. Now, when you take a look at this, interestingly, we used three basic data sets. All of them are publicly available. The data set on votes and that of CMC is a popular data set that most people are, almost all of you are aware of already. Switch, we chose it because there is a tendency for recommended system also as part of this. Our observation is that C5.0 tends to work a little better for all the measures that were considered as compared to NB. And the probable reason for that is because the new attributes that we added to the data set is not independent of the original data set. It is based on the exception, which may have some implications already. Next. So this is a preliminary work, and that's observations we've made so far, but there is a more detailed work which will be published in future papers, and so you can be on the lookout for that one. But if you want extra information on this, I'll be around at the poster section. Thank you.
Yeah. Hello, I'm Christian Daniel, and the work I'm presenting today is a joint work with Gerhard Neumann and Jan Peters. And together we are interested in reinforcement learning algorithms for real robots. So what that gives us is that we are also need to find methods that work with continuous states and actions, for example. And once we have that, next slide please, we have methods that solve tasks, but as we go into the real world, we realize that solving a task with one solution is often not enough. So for example, if you look at tennis again now, we see that playing tennis, it's not enough just to learn how to play a forehand to return a ball. But if you want to successfully play tennis, then you also need to know how to smash or how to play a backhand. And also going back to what Vincent said before is that often if you learn only one solution to a task and the environment changes, it may happen that the solution is unavailable. So for example, if you think about finding a path from point A to point B, if for some reason this path is blocked, you're lost, you cannot go to point B anymore. And instead, what we propose is that basically we enable our learning algorithms to learn multiple solutions to tasks and to learn them simultaneously. Thank you. And the way we propose to do this is by basically expanding our policy from a flat policy to a hierarchical policy. So usually on the left you see what traditional methods would do, that basically you have a state, and given that state you would select an action. And instead we propose now that we say, okay, we have a state, and given that state we select a discrete option that basically defines what kind of action we want to take. So if it's going to be a forehand, a backhand, if you want to go route A or route B. And then when we selected this option that we want to follow, again, we have this option policies, these sub-policies, which then define our actions given the state and the option. So we applied this to this game of tetherball. And you see here a Barrett WAM, a robot, a 7 degree of freedom robot. And the task is to hit the ball on the string such that it hits the target zone, which is behind the pole. So basically, you have to hit the ball around the pole. And the thing is, here again, you have these two options. You have two possibilities. You can hit around the left or the right side. If you would just basically take the combination, you would hit the ball straight into the middle of the pole. And what we could show is that we basically learn both solutions, so that the robot can really either hit to the left or to right. It's all learned together. And if you were to block one side, the robot could still hit around the other side. And the next slide. So what we present is basically a mathematically sound framework which automatically learns multiple options to a learning task. And what we could actually show is that it does not only learn multiple options, but actually because we're able to disambiguate between these options which might not basically be able to work together, like going around the left or the right side, we're actually able to learn a little bit faster, and on average we learn also better solutions. Thank you.
Hello, my name is Mark Deisenroth. I'm going to present some work jointly with Peter Englert, Alexandros Parashos, and Jan Peters on imitation learning by probabilistic trajectory matching. So in imitation learning, we are interested in kind of recreating demonstrated behavior by, so for example, you can imagine a human demonstrates a behavior, and we want to have the robot to do something that looks very similar to the demonstrated behavior. There are several classical methods of dealing with this. So one is inverse reinforcement learning, and one is behavioral cloning. But they kind of do a detour of solving this problem, take a detour. So inverse reinforcement learning tries to learn or infer the cost function of the human, and then afterwards tries to find or make the robot minimize this cost function, and then basically hope by minimizing this cost function to generate a trajectory that looks similar to what the human did. Behavioral cloning solves a supervised learning problem, but it's also an indirect way of solving this problem. Our approach is to directly try to solve this, say, similarity problem that we have in there by minimizing some sort of distance between a demonstrated trajectory and the robot's trajectory, and we can learn a robot-specific controller by doing this. Okay. The problem with with real systems is that if we demonstrate things a few times, we have a lot of noise in the demonstrations. We need to account for this. And also, if we have a robot and we have a model of the robot, we have uncertainties in this system as well. So there are two types of uncertainties in the model. So model uncertainties, because we are uncertain about the model itself, and also stochasticity in the model. So that's the reason why we need probabilistic trajectory matching here. We approximate the demonstrated probability distribution over trajectories by some sort of Gaussian distributions, and we do maximum likelihood estimation of the Gaussian parameters, mean and variances. And for the robot trajectory, we use Gaussian processes and predict them long-term ahead. So we do approximate inference for creating these predicted trajectories. And then the objective in our imitation learning setup is to minimize the KL divergence between the probability distribution over predicted trajectories and the probability distribution over demonstrated trajectories. Okay. The nice thing with this, and also with these Gaussian approximations in there, is that you can write down this imitation learning cost function of minimizing the KL divergence between trajectories as the sum of individual KL divergences at each time step, between probability distributions at each time step. And if you want, you can consider this a reinforcement learning cost function with a naturally induced cost function. Usually if we do reinforcement learning, we write down some, for example, some squared distance between a set point or so. But in this case, if we just take this reward function to be the KL divergence between two state distributions, then we can phrase this imitation learning problem as a reinforcement learning problem, and we can use reinforcement learning algorithms to solve this imitation learning problem. In this case, we use a model-based policy search method to solve this imitation learning problem by indirectly by reinforcement learning. And we applied this to table tennis hitting movements. We have a tendon-driven robot. So we have a robot arm that is driven by tendons, has a lot of springs. It's really nasty to model. But we have a demonstrator who demonstrates how to hit a table tennis ball in this setup. And the robot can, by using this imitation learning with trajectory matching approach, can very closely imitate this behavior. So the demonstration is shown on the top, and the imitated behavior is shown on the bottom. And the only thing you should see is that they're very similar to each other. And we have also other applications, but I think this is the most interesting one. Okay, if you want to know more about this, please come to our poster.
Hi, I'm Jessica Scroof. I'm from the University of Liège in Belgium, and I will present you Pronto, the pattern recognition for neuroimaging toolbox. So this toolbox aims at linking the machine learning and the neuroscience communities. So during the past decade, machine learning models have been more and more used to analyze neuroscience data. There are a few softwares existing, but they are not fully flexible, or they require programming skills, which often psychologists or medical doctors don't have. So here, the aim was to build a software that would provide a framework for them to analyze the data using machine learning models. So the software is organized in 5 main modules. So you have the inputs on top and the modules in blue. And they are really classic models with data and design, feature set, specify model, and run model. They are designed to be really flexible, so they could consider any problem. And we have outputs and optional review options. So in the, next, please. In the user point of view, we have graphical interfaces. So you can see on the left the main window, in the middle the results window with the predictions on top and the weights of the linear SVM model. And so these are button pushes, so they like it. But we also have a batching system on the right. So this was developed by Volkmar Gloch, and we are using it in MATLAB to help people that already have a certain background in programming to automatize some analysis. But I guess you're not potential Pronto users, but more likely to be potential contributors to Pronto. And so that's why it's also important that we are here presenting the work. So what we have now is something with SVM, Gaussian processes. So it's basically, it's nothing new. It's just that we need to transform all the inputs and to have these models to be applied to neuroimaging data, which is a specific problem. But when you develop algorithms for machine learning, then it might be really interesting to have them tested on this kind of data. Because, well, it's a completely different world, but it could be useful. So we developed the toolbox to be also easily contributed to. So we use machine libraries. So if you provide the library with all the inputs it needs and the outputs it provides, then we can easily put that all in Pronto, and it would be made available to the neuroscientific community. So if you want to know more and maybe to contribute, then you can comment the poster. Thank you.
Hi, I'm Balázs Pintér, and this is a joint work with András Lőrinc. We are from the Eötvös Loránd University, Hungary. And the challenge we address here is how to bring together a transdisciplinary community and how to help them create knowledge. Currently, we work with 2 communities, one in robotic surgery and one in education, and we help them, we support them by providing intelligent features through a web portal. We help them create new knowledge by collecting lots of information from the web for them to start with, and we help them understand each other because, for example, in robotic surgery, there are roboticists, surgeons, lawyers, and of course the patients, and they don't understand each other's terminology. So what we do, we explain it to them using natural language processing, and we also verify knowledge. Next slide, please. So here is a high-level architecture. The main component is a concept repository. This contains all the knowledge. It's basically a wiki like Wikipedia, and it's fused together with an ontology. And it is in constant interaction with our AI component, the concept AI. There is a feedback loop between these. So if users add new content, it will be used as in the data set of the AI, and the AI can also correct the data set. So these 3 components, the community, the AI, and the concept repository can evolve together. Next slide, please. And we have a system for quality assurance that emphasizes, on the one hand, openness, and on the other hand, high-quality knowledge. So anyone can contribute just by registering. They can start to write and edit these so-called drafts. And when a draft passes through a voting process and also decision by an editorial board, then it can become a peer-reviewed article that contains verified knowledge. And the system is completely open. It is based on merit. Contributors can collect points. And if they have enough points, they can become a member of the editorial board. Next slide, please. And lastly, our intelligence. On the left is the concept repository. It's basically an ontology where each concept is grounded in text. So for each concept, we have description. It's a wiki page. And also, we have lots of examples, a corpus annotated for each concept, and these are expanded continuously by the community. For symbol grounding, we have an algorithm based on structured sparse coding. Here we match the structure in structured sparse coding to the structure of the problem. So we have a very robust algorithm. It's more robust for this problem than support vector machine. And it can work at very large scales with thousands of concepts at once. And we hope that these communities will continue to evolve. We are just starting them, one in the Eurosearch project and one in education. And if you would like to contribute, you're welcome. Thank you.
So, hello, I'm Theodore from, right now I'm New York University in Abu Dhabi, but this work was done while I was in Demokritos, the research center from Greece. This work was published in EUCogIII 2012, and this is a follow-up paper regarding, in general, object detection, but right now we'll be tackling the problem of human detection from laser data. So next slide. So this is our robot. It's a conversational robot, and hence there is a necessity to understand the environment and especially the human presence. So I'll say some things about the challenges that 2D laser scanners face. So in general, when there is nothing happening, you have some continuous topological manifolds. But of course, there are several environmental problems sometimes. For example, occlusion is one of them that creates several gaps within these manifolds. And one more problem is the speed changes of humans within the environment. This causes, of course, an alteration of sparse and dense data, and all of these cause several problems in the clustering process. So next slide. This is the pipeline of the algorithm. Practically, we contribute at the level of representation, and hence we try to overcome several of these problems. So in the first place, we don't deal with the problem in a frame-by-frame representation, but we take it in a time window, let's say for 1 second, and you can see in the first picture, the height is the time dimension, and all the data are projected in this artificial space. So this space practically has a lot of properties that help us deal with the clustering process. So in the second image, you can see the spectral clustering results. And the red and the yellow are two humans, where the other two objects are static objects. And there you can see several occlusions in the blue static object. And also you can see the difference of the red and the yellow objects that are humans and move. So from these images, it's pretty distinctive which are the objects and which are the humans. The third image is after the clustering process, we need to model these objects, and practically we interpolate by a surface. This surface is a true mathematical function because the laser, due to occlusion, ensures that 2 points cannot be at the same level and beam. So this model practically models both motion and shape, and this is an improvement over the literature. So in the end, we have a mathematical representation of both model and shape of humans and non-humans. And from these models, we extract features. So the final stages are, before. So it's the last two boxes above. We convert these mathematical representations into images, and because they are surfaces, we want to study practically the curvature of these surfaces. So it's natural to apply histogram-oriented gradients. Of course, there are several other features that could apply. And at the last step, we just apply a classification algorithm. For now, we used a naive Bayes. Please go to the next slide. And also a GMLVQ, which is an extension of LVQ, where there is also a metric learning. So from the above table, from the upper table, you can see the results between GMLVQ and naive Bayes, with and without PCA preprocessing. These results show us that for GMLVQ tends to overfit several times, and hence there is a huge classification error. Naive Bayes seems more natural. However, with PCA is much better because it ensures the orthogonality and independence that naive Bayes wants. And the table below is a comparison with the state of the art, which is work done by Spinello. We tried several combinations of Spinello's features and classifiers and stuff. We seem to be on a par with the state-of-the-art result. Next slide, please. And to conclude, this work is, according to my opinion, really important because it cannot be applied only to the human detection problem, but in general object detection and recognition, because it contributes to the level of representation and not only in the feature phase or the classifier. So due to that, we have supervision at the level of real-world objects and not in a frame-by-frame thing, so it's much more meaningful. And all of this, yes, help us in reasoning on the sensible world, which is, it can offer natural fusion between other sensors and more holistic approaches when you use object context. Thank you very much.
I'm Daniel Repko from INRIA Lille, and I'm going to talk about time series information in unsupervised learning, and which is a very recent work of mine. And also, I must say I'm a mathematician, so please bear with me. Next slide, please. Okay, so we have the following problem. We have a time series x1, x2, and so on, and where xi come from some high-dimensional space. And we want to find a representation of this sequence in the form of another sequence y, yy, y1, y2, and so on, where this yi are from some small low-dimensional space or just from a finite set. Okay, and what we want from the representation is that we preserve as much as possible of the time series dependence in the original sequence xi. And so why would we need this thing is because if then someone gives us some problem about this data, for example, someone gives us labels, or maybe someone gives us rewards in a reinforcement learning setup, then we would be able to solve this problem much more easier and faster because we have a much smaller space. Okay, so this problem can be sort of a dimensionality reduction with the focus on time series dependence. Next slide, please. Okay, so let's try to formalize this problem a little bit. So in an ideal situation, we would like to have a function f such that given f of xi, the initial inputs xi become conditionally independent. So given the f of xi, we would like to be able to discard xi. And so it can be shown that in this situation, finding the function f that achieves this property amounts to maximizing a sort of functional, which is the time series information here, which is h0 of f of x minus h infinity, where h0 is a zero-order entropy of f of xi, and h infinity is the entropy rate. So H0 is how random the sequence looks if you discard time series dependence, and H infinity is how random it looks if you know and learn perfectly well all the time series dependence. So it can be shown that under this conditional independence condition, the function that is the best representation maximizes this functional, the time series information I infinity of f. And so this basically allows us to formulate the problem that given a set of functions f from x to y, we would like to find the function that maximizes this functional. Okay, and so what it is very important is this functional I infinity of f does not involve, to evaluate this functional, we do not need to consider or model the distribution of the original time series xi. So if you want to estimate this thing, we only need to work with the representations f of xi. Okay, and so I can have some learning theory style results about this, basically that shows that empirically you can find this quite easily if you just maximize instead of the theoretical function the empirical version. Thank you.
Okay, hello everyone. Can you hear me? Okay. So hi, I'm Gergely Nagy, and I work in Budapest, and I work with two other Hungarian guys, Csaba Szepesvári and András György, who already moved to Canada. So we are mainly interested in reinforcement learning problems and online learning problems, and this work that I'm presenting here is a mixture of these two settings. So it's essentially it's a reinforcement learning problem where the reward functions change over time, and they can change without making any assumptions about the nature of the change. So it's kind of an online learning problem. So let me describe just vaguely how this process looks like. So there's a player interacting with an environment. So in each round of this sequential decision process, the player selects an action. And based on this action and on the complete state of the environment, it receives some reward. And its goal is to maximize this reward. So we are interested in some specific structures where the environment can be decomposed into two parts. One part that is controlled and has a good stochastic model, and this is a Markovian dynamics. So this is the stochastic dynamics here. And there's another part of the environment that you have no model about, and you cannot even hope to model it. So this is where this online learning component comes in. Can you give me the next slide? So in this setting, when you make no assumption about the sequence of reward functions, it's traditional to try and minimize the regret. So the regret is the difference between the performance of your algorithm, so the total reward that your algorithm gathers. So this is R hat t in this case. So these are the total rewards that you receive. And the other thing that you compare it with is RT of pi, which is the total reward of the best possible policy given the sequence of actions. So essentially, we are interested in algorithms where you can theoretically guarantee that this regret, this gap between the best performance and your own performance is small. And you can look at this problem from a number of perspectives. So you can make a number of assumptions about the structure of the stochastic dynamics. For example, you can assume that it's an episodic structure. So in a setting, when you start in each episode, you start from a starting state, and an episode terminates when you reach an end state. But you could also assume that there's a continuing task well, it never ends, but in each time step, the reward function is allowed to change. So, and there are also some assumptions that you can make about the feedback given to the learner. So the first column considers the case when after each episode is terminated, for example, you can observe the whole reward function for that episode. So this is called the full information setting. And there's a much more complicated setting when the learner only observes the rewards that it received during that episode, and this is called the bandit setting. And also, on the columns, you can see two different versions. When the agent is assumed to know the transition probabilities, so it doesn't have to estimate them. But here's a more difficult problem when it is unknown and you have to estimate it from samples. And so in this setting, you have a very interesting combination of stochastic learning problems and adversarial learning problems. So we have a number of results for all of these settings. But as you can see, the last most complicated one is still not solved. But, well, the other things are also pretty much involved. So that's what my PhD thesis is about. It's about 150 pages, and all we have there is these proofs. So if you want to hear some details, then come to my poster and check it out.
Hi, I'm Jan Rupnik from Josef Stefan Institute. This is joint work with Andrej Muhic and Primož Kraba. So our main focus here is modeling collections of multilingual collections of documents. So here the goal is to find like multilingual topics so that we can use them so that we can represent all documents in a single common space. So here is an example. We have documents in English, Slovenian, and Hindi. So we have a comparable corpus, let's say Wikipedia, and we have a lot of links, a lot of pages between Slovenia and English, and between Hindi and English, but there are very few pages between Slovenian and Hindi. And the goal is to find some mappings, P1, P2, and P3, to a common space so that it will preserve, let's say, the similarities will be preserved semantically. Next slide. So here our modeling assumptions are, so we use representation is vector space, bag of words model for each language. And our main observation in Wikipedia was that usually the links are not missing between language and English, but between certain languages they are many times missing. And here we exploited this fact, so we modeled it, we focused on relationships between English and other languages only. So here the first step was to reduce the dimensionalities, and we approached it by doing a SVD, the composition of a set of covariance matrices between English and all the other languages. So this is the red column, and so this can be done very efficiently, and it reduces the dimensionality. But the problem here is that this, when you decompose this topic matrix of the other languages, you don't have any guarantees about orthogonality or anything like that. So that's why we do another step. So next slide. So here we also, here we wanted to find this refined set of these linear mappings that will maximize the sum of squares of correlations. So here we're maximizing the linear dependence between these representations, and using, again, these assumptions that the English is a hub language and most of the information is always available that goes through English, we could reduce an otherwise difficult optimization problem to an eigenvalue computation, which then made it feasible. So these two combinations of these two steps enabled us to find these mappings. So next slide. Yeah, so this is my final slide, and it's about our evaluation. So here we had 8 languages, some English, Spanish, Russian, Slovenian, Hindi, and then some Varai, and Piedmontese, and Haiti language. And the thing to note is the lower table shows how many documents there were available for training. And the interesting ones are, for example, Hindi and Piedmontese, where we had 0 training documents. And here our assumption was that even though there are 0 documents, all the other alignments can help us to find a representation that will that can be useful. So, and we evaluated it on the task of information retrieval. And the upper table shows us that, for example, Hindi and Piedmontese, we get, so 0 would be random information retrieval and 1 would be perfect. And we see that we get decent results even in the cases where we had 0 training available. So if you would like to hear more details, come to the poster.
Hi, so I'm from University of Saarland, and this is a joint work with that experimentative. My name is Ivan Titov. So I'm going to talk about a project on learning meaning representations for natural language. So why do we care about meaning representations? Why do we care about semantic representation? So consider question answering problem. So you're given a question about the knowledge contained in a collection, and you want to find an answer. But the problem is that the answer can be worded in a very different way from the way it's worded in a question. So you want to understand, for example, in the first case, that block and suppress mean essentially the same thing in the biomedical context. And to do this, we want to induce a form of semantic abstractions which isolates you from this language variability. Yes. OK, and so more formally, what we want to do, we want to give an input which is basically a text. We want to predict semantic graph, which defines what kind of situation we have. So in these examples, we have a winning prize situation and what kind of participants and properties of these situations we have verbalized. And in general, these are very, very simple examples. In general, graphs are much more complicated. They don't necessarily need to be trees and can be very large and recursive. So we want, no, not yet. So basically, you can think of this task as a type of clustering and decompositions, because as input, you are given a sequence of words, but you're also given a syntactic dependency tree. So basically, black part of this graph is provided as input, and the colored part is what we want to predict. Yes. And we approach this problem by defining a joint model of syntax, semantic, and lexical information. So lexical information is basically words, and perform inference within this model. So we approach this task by unsupervised learning. So why unsupervised learning? Because basically the two other alternatives, supervised learning or basically defining rules, don't provide enough coverage. So resulting models end up being very domain dependent or don't cover many words, many lexical phenomena, because semantics is very tied to lexical information. And another point, we approach this by Bayesian learning, by non-parametric Bayesian learning. So there are a couple of reasons why we choose this methodology. So one reason is we want to handle accurately the uncertainty. And uncertainty and ambiguity is something which is inherent in natural language. So we really want to account for uncertainty quite well. And another reason, we want to have a principled way to encode some prior information in the model. And non-parametric techniques allow us to avoid having model selection heuristics, providing more elegant solution, I would say, to this problem. Okay. So we evaluate our model in two different setups. First, showing that this model of semantics help in the question answering setup. So actually, the example I had in the very beginning of my talk is actual answers by the system. And in the second case, we evaluate how well our result compares to what linguists think about semantics of the languages. In both cases, we get quite favorable result, generally outperforming all the alternatives. And we also look into a couple of extensions. One is induction of cross-lingual semantics, and not only to induce cross-lingual semantics, but also to improve models for every language, because languages have different problems, and you can expect that inducing semantics simultaneously across languages might help. And another point is to encode some of the supervision, use a little bit of supervision to improve learning. Obviously, unsupervised learning has its own problems. Some of the phenomena is hard to learn in unsupervised setting. So if you want to know more details, come to my poster. Thank you.
Hello, I'm Peter Auer from the University in Leoben in Austria, and I'm going to tell you about our work on autonomous learning, meaning that learning without immediate goal. And this is funded by Pascal and the Complex project. So please. So the motivation is that humans and animals apparently exhibit this kind of learning where they explore the environment without immediate goal. And we want to come up with a model which gives us some handle on analyzing such behavior. So this is a very particular model, but if you will see that the algorithm actually shows some interesting properties, which, yeah. So our setup is that to be able to do some analysis, we assume that we have a Markov decision process without rewards and reset to a safe state, like lying down if you want to learn to walk. And the goal is to find policies, strategies to go to all possible states which are reachable in a certain vicinity of this neutral state. It turns out that formally this is too ambitious, so because there might be states which are reachable only by going through intermediate states which are not really explorable or reachable. So we need to make an additional assumption which says that these states can actually be explored incrementally. So which means you can go to a state Si by using only policies defined on previous states. So this allows for an incremental learning. And in this case, we come up with an algorithm which is called UCB Explore, and which generates policies to all these states in a reasonable time. And the next slide shows you this algorithm. It has, in each iteration, it has 3 steps. So first, so it maintains a set of known states for which you already know how to go there. Then you look at all the neighboring states of these known states. From these, you pick the one which is the easiest to reach, assuming an optimistic model of your environment, modular the experience you have already made. So you pick this easiest state, try to go there, calculate a policy to go there, and then there's this evaluation phase where you actually try, does this policy indeed work? If it works, well, you have a new known state. If it doesn't work, you have learned something about your environment because you know your optimistic assumptions were wrong. And so this algorithm has 3 nice properties. So it does this incremental learning. It sees only a small part of the environment and incrementally increases this known part. It selects for the next step the most promising goal, which is most promising to be actually reachable. And it does a testing of its current knowledge by trying this policy if it actually works. Thank you.
Go ahead. Keep going. To the end. Yeah. And back one. So I'm going to talk about some work in my group at the University of Stuttgart. We work on multilingual processing, which was aimed at acquiring the training data to solve translation tasks. So I think most people are aware that Google Translate is implemented as a structure prediction problem. It's supervised learning on very, very noisy training data. And I'm going to talk a little bit about different kinds of work that can be used to acquire better data. So the first slide is this problem of transliteration mining. So we just saw a few presentations ago the interlingual links in Wikipedia. It turns out that using unsupervised learning, we can learn very good models of transliteration directly from this graph structure. So if you look at the examples up there, you have English and Hindi. Some of the English words are transliterations of the Hindi, which are nicely phonetically written out for you to the right. And the goal of this task is simply to automatically separate the ones that are transliterations from those that are not. Next slide. We've also been doing a lot of work on new models of translation. So many of you may be aware that Google Translate uses sequence prediction, but there are now 2 schools of translation models, sequence-based models and hierarchical models. The problem we've been working on is the problem of long-distance reordering. This is the problem that, for instance, the clausal structure of German
is very different from the clausal structure of English. And we're using classification-based approaches to do this and integrating these into machine translation decoders. So for sequence-based translation, we've switched from the so-called phrase-based MT, which involves memorizing chunks of words, to Markov models over smaller units. And in work on synchronous context-free grammar decoders, we've been looking at how to better define the models used to do long-distance reordering. Next. And so two other things that are on the slide that I didn't talk about. One is discriminative re-ranking for syntactic parsing, which is morphologically aware. And the other one is predicting the morphology of German when translating from English to German. This work is also applicable to French, Spanish, and hopefully in the future to Slavic languages, which are even richer in morphology. And so if you'd like to see some more details on this, please come and see our poster. And I'd like to thank Pascal as well, because it's been very helpful to my group.
Hi, my name is Giovanni Zappella, and this is a joint work with Nicolò Cesabianchi, Claudio Gentile, and Fabio Vitale. In this paper, we present algorithms for link classification. Next slide. First of all, what is link classification? Let's suppose that you have a social network, and you know that some people in the network are friends, some other people are enemies. So given to people in the network, you want to predict if they are friends or enemies. And we model this problem as a two-cluster graph, where nodes in the same cluster are connected by positive edges. Edges, those have a +1 label, and nodes in different clusters are connected by negative edges. And we assume that these labels are consistent with two-cluster structure with a probability of at least 1 minus p. And we work in a transductive active learning settings. That means that we know the topology of the graph in advance, and our algorithms can select their own training set. So, next slide. We can prove some theoretical results, and one of these algorithms has a basically optimal upper bound on the number of mistakes. And we find the different trade-offs between the number of requested labels for the training set and the number of mistakes during the test set. And another special case that can be interesting is when a graph has a small diameter. This is quite common in practice. And in this case, we can show that just using a breadth-first spanning tree and a simple multiplicative rule, you can do your prediction with pretty good results. We tested these algorithms on real-world, next slide, please. On a real-world data set coming from social networks like opinions, Slashdot. Those are created by the users, and we got pretty good results comparing our algorithms with much slower and passive spectral heuristics. And using just a tiny fraction of their training set, we were able to be competitive or outperform our competitors. Thank you.
Hello, I'm Naimi Lim. I come from University of Évry, and this is a joint work with Yassin Senbabaoglou, Professor George Michaelis from University of Michigan, and Florence Achebuk from INRIA. So we are interested in the influence of regulatory networks, and especially gene regulatory networks. So this is a network that you can see on the right side. So we start from gene expression data that you can obtain from DNA microarrays. And so you have this time series, this multivariate time series that measure the expression of each gene at different time points. And from this data, we want to retrieve the network. Next slide, please. So there have been lots of models proposed by many fields of mathematics over the past decades. And some of them have face some problems. So for instance, for correlations, we only have undirected graphs, and we lose directionalities when we want, in fact, causal networks. And for instance, for Bayesian networks, the problem is that they are very time-consuming if we want to scale up. Next slide. So here, what we are going to do is that we will model the transition function that predicts the gene expression at time t+1 from gene expression at time t with a model H. And this model H is non-parametric. You can next. So what we are going to use is what we call an operator valued kernel that extends, in fact, linear properties to nonlinear properties. These operator valued kernels are more general than scalar kernels to predict vector valued functions, for instance. So next. So what we are going to do is that we will learn this autoregressive model from the data. So we have to learn the C's that are the parameters of the combination and the parameters of the kernel. So next. And to retrieve the network, what we are going to do is to compute the Jacobian of this model that shows the cross influences of each variable through time, and then threshold this Jacobian to get the network. And to improve the performance of our model, we are putting this in a boosting procedure. So we applied our method on a dream challenge where participants have to find this kind of network. As you can see, there are modules and hubs, so this is a very difficult problem. And we see that our method outperforms existing methods. Next. So thank you, and if you want more details, come and see my poster.
This one, thanks. Okay, sorry about that. Okay, we are solving the problem of data or information visualization of projecting extremely high-dimensional data into two-dimensional scatterplot types of displays, an example of which you see here. So it's clear that we can show everything there, and the big problem is how to formalize this trade-off, and we have been able to solve that earlier in cases where we do know what actually is it. So if we know the input space metric or which points are similar, then everything works. So the problem we assume the users are having is finding similar points which we are interpreting as an information retrieval problem giving the display. And how we solve this if we know the input space similarities is by just assigning costs to false positives and misses, which would be similarities that you cannot see on the display because the display is low dimensional, it cannot solve all. So we assign the costs, and then we have a well-defined cost function, which we then just optimize. Right, so this works well if we know the distances. But here we are trying to take the baby steps to the direction where we do not know the distances. So we have to actually ask somebody, and we decided that let's build a kind of baby cognitive system that asks the user. So the user browses the points, and when he hovers the mouse over a point, he gets more information about the specific point. The variables in general, but in this case they were documents so that we can actually show some things of the abstract. And then when the user detects that actually these points should be closer together or should be further apart, then he gives the binary feedback about this. And then we learn metrics based on this feedback, and then we, of course, can again apply this system that we have given known distances. And now the task is to make this converge with as little user feedback as possible. And right, the rest is done with probabilistic modeling. There's obviously lots unknown in the method. We only have very little data, very little feedback. That's the difficult problem. And of the authors, I'm the last one. I'd like to thank the student, Max Sandholm, who we are supervising together with Jakob Peltonen, and I am to be blamed of adding the link there to a university that has changed names twice, and this doesn't work anymore. Thanks.
Okay, thank you, Jan. Hello, I'm Nicolas Serrano, and I'm from the Universitat Politécnica de Valencia, and I will be talking about this last challenge of Pascal 2. This is called the ISD challenge that comes from interactive annotation of sequential data. Well, the motivation of this challenge is because video lectures are being recorded nowadays everywhere. I think that we are being recorded right now than in other conferences in university courses. And it's great because we can access these lectures freely from everywhere, but the videos themselves are not enough because we need also the transcriptions of these videos. So we can perform some indexing or maybe search within the contents and access to the specific point in the video in which what we want to hear is talk. So the problem is that obtaining these transcriptions is very time consuming and very expensive, manually obtaining them. And well, a solution is to employ an automatic speech recognition system to obtain an automatic transcription. But again, the current systems are far from perfect. We are obtaining, I think, that from 20 to 40% of error. So what we propose in the Translectures project is like fusion of the best features of both approaches, manual, the quality of manual transcription, and the scalability of and speed of automatic systems. Again, the problem is that we want to employ the least user effort as possible. So don't bother the user at all, only a little, and employ its interaction at its best. Well, this is a diagram of our current approach. Basically, a lecture is recognized by an automatic speech recognition system, and then some of these recognized words are passed down to the user that supervises them. And by supervision, I mean that he corrects them if necessary. If they are okay, so he says, okay, they are good. And then these transcriptions can be used, they have been improved, and also they can be used to adapt our current system and possibly improving the recognition of next video lectures. So, well, again, you will see that this is kind of related with active learning and all this kind of techniques. Well, in our challenge, what we do is to simulate this the interactive approach in videos from videolectures.net. So what we do is we select some videos and we split it, each of them in two parts, in block 1 and block 2, that is with B1 and B2. Well, then we will perform some user supervision limited the user only supervised the 20% of the words. And then we will use these words to improve the baseline system and recognize B2. So B1 is improved by the user itself, but B2 is only improved by the system that have been improved from these supervisions. So, well, the participants in our challenge, to extract them from all the details of automatic speech technology, what we do is that we gave them the word graph that represent the hypothesis of the system, and they have to calculate some features and tell the system which words they want to supervise. So this makes easier for them to understand all the system. And all the other steps they're performed by an oracle. The supervision itself is simulated along with the system adaptation and the posterior recognition. Well, I will not go in much detail about these results. We were successful. We got almost 90 submissions from 8 participants. And well, from this table, we can see the results. The first row is the original error when no supervision is applied. At first, we have 30% of error in B2, in B1, and we can see that once this 20% is corrected, they were also improved. The first 3 rows were obtained by us. The random is like the worst approach because it randomly supervises words without any kind of calculation of features. And you can see that all participants also improved this baseline along with almost all of our results. The oracle results is a method that knows the reference, so it's kind of the best case that could be obtained. Well, and also you can see more details in our posters. And now my colleague Alphonse Juan, because this is the coordinator of the Translectures project, will be giving the winner certificates.
Okay, on behalf of the challenge supporting organizations, it's a Pascal II network, EUCogIII network, Translectures project, Universitat Politècnica de Valencia, Knowledge for All Foundation, and Institute Josef Stefan. It's a great pleasure to give our winner certificates to Pavel Golik from the University of Aachen and Thierry Artertz from the University Pierre et Marie Curie. So, let's go.
Two of the winners give their spotlights on their methods.
Okay, hello. My name is Pavel. I'm working with Hermann Nei's group at our WTH University in Aachen in Germany. And this short talk we're going to spot my approach to this challenge. So what we already seen, the task was to reorder words from a hypothesis of a speech recognition system in order to spot the ones that were most probably misrecognized, and then reorder them in a way to push them on top. So if we have some supervision mechanism, like Oracle or human supervision, if they fix the errors, if they correct the errors, we're going to improve our system by performing adaptation. And it's a natural thing to think about some way of describing the uncertainty, and this is often referred to as confidence measures in speech recognition. We want to find some some confidence measure. That's basically it. And the challenge was in some kind of a restricted environment. So we didn't have access to the ground truth. We only had access to an online evaluation oracle or evaluation tool. And that was difficult to decide on the right thing to do. So the best strategy I could think of was just to take the baseline and then carefully move around and see how sensitive different parts of the system is. So I'll basically tried out two things, and I'm going to talk about confusion networks and posterior scaling. Next slide, please. Confusion networks are a different representation of lattices or word graphs. There are lots of publications in the last 14 years or so on confusion networks, and there are lots of pros and cons. One thing why I was thinking this is interesting for this task is confusion network can be more closely linked to a word error rate, which is the measure of the system quality in speech recognition tasks. And it's not that easy to find a unique or a correct way to construct a confusion network from a graph, but usually we just, happily I had a tool that already implemented this conversion. And this is what it looks like if you just switch from the lattice, where you have different timestamps, to a discrete representation where you have only positions in a sentence. Next slide, yes. And the other thing was posterior scaling, which is a way of just increase a resolution in a region where you think the posteriors, confidence measures are important. And I was thinking that words with low confidence are most important, so let's try to increase the resolution. And then you can find some nonlinear function that performs basically that. There are two parameters that I had to guess. If I'd have an access to the ground truth, I would probably optimize them, but this is just a good guess. And on the next slide, there is a plot that shows what the nonlinear scaling does. It just pushes the low values a little bit higher and increases the resolution in that region. Well, and as you can see, it works well, probably not as good as the next solution we're going to see, but good enough for the third place. Thank you very much.
Hello. So I am from University Pierre and Marie Curie in France. Okay. And as you may understand, this challenge was difficult in that we had no the ground truth, and that when we submitted one trial, so it was basically one submission was a ranking of about 20,000 words from the first to the last to ask for manual labeling. We had to wait about 10 hours or something like that, or 12 hours, I don't remember, so that the system is retrained. The acoustic model are retrained so that you can get an error. So we didn't have the possibility to tune very much the systems and to try very complicated methods. Actually, I began by using, I would not say smart, but smarter than what I used later, methods, and I had very bad results, but I had no time to make a number of submissions. So this plot is the plot of all my trials, where you see on the x-axis the performance on the block 1 set, which is the block of rod graph on which the system is retrained. And on the ordinate, you got two series of points. One which is increasing steadily with the axis, which is the performance on B1 plus B2, which is the measure that were used for determining the winner. And at the top of this graph, you have something which is more or less constant, which is the performance on B2, meaning that you can try to learn on B1 using information from B2 to be able to generalize what you have learned, but it's very difficult in that case. Okay. Okay, so basically what I did is using some simple metrics of entropy to determine parts that was the most ambiguous. Okay, so but we have there are many ways to compute entropy in such a world graph. You get an example of a true world graph from the B1 set on the left. So you got lots of hypotheses with lots of edges which correspond to the same word, but not exactly with the same time boundaries. So you have lots of possibilities to determine an entropy measure, which correspond to an uncertainty on the labeling at a given time in the graph. So I used a number of measures of uncertainty based on such an entropy definition. And please, next one. And then this gave already some good results, better than the baseline. And then I combine two methods, one which is based on a tutorial that was proposed as an example method by the organizers. And it is a method inspired from the organizer's method, so it's not the organizer's method. And this method by the entropic measure. So I got two rankings of the words, the 20,000 words that I want to label, maybe. And I use a mix of the two rankings. And using a mix of the two rankings, I can optimize the final word error rate on the block 1 on the block 1 plus block 2 sets. And this shows how the performance behave on the B1, B2, on B1 plus B2, but I will give details in the poster. Okay. So as a conclusion, I would say we have limited improvement with respect to the organizer's baseline. So either we did not imagine very efficient methods, or the baseline was good already. But one difficulty was it was we didn't have many runs possible. We couldn't train the model and see how it happens before submitting it because we didn't have the run truth on any word graph. So it was a particular kind of active learning with a kind of one-shot active learning where you have to decide in one shot all the order of all the words that all the samples that you want to ask the user to label. So I don't have actually a main conclusion of that. I'm not sure. I would say for active learning, maybe using diversity and using few criterion to select samples is basically a good idea, but I didn't see that in my experiments here. Thank you.
Thank you.